and the foremost thing that you need to know is, and you need to be able to define isotopes. So define isotopes. What are they? I'm pretty sure you've learned this, you've heard this, you can say this and recall the definition by your sleep. So what are they, right? What are isotopes? Let's get to it. Alright, so isotopes are atoms of the same element. Element that contain the same number of protons, and we know that proton number from the previous video, that proton number is also known as atomic number, right? The same number of protons and but different number of neutrons. And previously in the video, we learned that mass number is proton number plus neutron number. So if the neutron number is different, that altogether results in a different mass number. So these are alternate words and alternate ways you can describe isotopes. You don't have to say specifically mass number, you can say number of neutrons. You can use them interchangeably. Alright, so this is a definition that they want you. It's usually a 2-mark question when they ask you to define what isotopes are. So that's the first point done. Let's talk about interpretation and presentation of isotopes using symbols. Alright, so if you have, for example, the same example you've been given here, we have carbon with a 12 and a 6, alright. We know the bigger number is always your mass number, and your smaller number is your atomic number, also known as your proton number. Alright, so you need to be able to interpret the symbols. Now, if I say my isotopes of, let's say, chlorine, I can write my isotopes of chlorine as a Cl 37 and a Cl 35. You see here, I could write the 17 here, but both of these chlorine have the same proton number, and they have of 17, so I don't really need to write this. So in order to represent an isotope, you usually want to refer to them by their mass number. So here, chlorine, if we know that chlorine has a proton number of 17, let's try to deduce, let's try to come up with and calculate the number of neutrons that chlorine has. Chlorine, okay, we're going to call this chlorine A, we're going to call this chlorine B. So let's use different colors, alright? So if I'm using chlorine, if I'm going with chlorine 37, so we know mass number, okay, is equals proton plus neutron. If I have my proton, so if my mass number is 37, equals my proton number, which is 17, plus n. I don't know my n, so in order to find my neutron number, I just subtract my mass number and then my proton number from my mass number. So that would give me 37 minus 17, which is 20. I believe. Let me just quickly get the calculator. 37, 17, 20. Oh my god, got that right. Alright, let's go for the chlorine 35. Use the same formula. Now we've already come up with this simple formula, which is N equals mass number minus proton number. Alright, so that would be 35 minus 17. So chlorine B has 35 minus 17, 18 neutrons. So this is your neutron number, this is your neutron number. Alright, so clearly they have different neutron numbers. So these are some representations. Now if we look at the symbol 3517 Cl minus, what does that mean? Okay, let's go put on 35 Cl Oh, sorry. Erase that. 17 and a minus. So we know, okay, this is an important note to take. I'm gonna use, okay, let's use this version of red, I guess. We know that in an, sorry, in a neutral atom, proton number equals to electron number, right? This is a recollection. So when this here, however, don't want to use the same color, sorry. So oh no, sorry, just highlight this. All right. So this here, however, is not an atom. All right, it's an ion. So it clearly will have a different number of protons and a different number of electrons. All right. So what does it mean? So initially you would expect chlorine to have 17 protons, right? However, because of its negative charge, that means it's let's go. Negative charge means it needs +1. All right, it's asking, hello, anybody give me one more electron. We know, why do atoms want electrons from other people, from other atoms? Because they want to fulfill their fuller outer shell electron. They want to fulfill that rule so that they are stable. All right, so chlorine here is asking, oh, I need one. So therefore, it would normally have 17 electrons, but it's asking for one. So now the actual amount of electrons chlorine minus has will be 18. All right. And if we want to calculate the mass number, the neutron number, N equals mass number minus proton number, which is 35 minus 17. We just did this earlier, which is 18. This is the neutron number and this is the electron number. Or okay, so pretty simple. Now if we have a positive ion, let's say Mg2 plus, and it has a proton number of 12, so that means when you have a plus, that Mg is saying take my 2. Take my 2 plus. I don't want this. I'm already so full. Take the food that I have. So whatever element it reacts, atom or element it reacts with, will take this too. So therefore, whether magnesium is supposed to have 12 proton, and 12 electrons, right? Normally, but the ion of magnesium, magnesium 2 plus, because it's saying, hey, take my 2 plus, it will be subtracting 2 electrons because it's giving it away. All right, this could be a bit confusing because normally if you have a plus, that is addition, but in this case it's magnesium saying, I don't want it, that's my additional, you can take it. So that would be 10 electrons. All right, so magnesium 2 plus will have 10 electrons. Okay, moving on. That's the first that's the second point done. So there we go. Let me use a different color. Let's do a little turquoise right there. Now let's talk about isotopes and the properties. Okay, isotopes will always have similar similar chemical properties. All right. Okay, this is you're supposed to know this, but how would you explain, why exactly is that? Why do they have similar chemical properties? I've used so many of these colors. Let me change it up a little bit. This is because they have the same number of protons, hence same number of electrons. Well, let's just say they just have the same number of electrons. That their electron number is not vary or change. Even if they're ions, they'll still have a 35, 37 difference in mass number and not in electron number. So they have the same electron number. So this means same electronic configuration. And when you're talking chemical properties, you're always talking reactions, right? So if they have the same electronic configuration, that means same valence electron number, valence shell. So in a nutshell, what I'm trying to explain and trying to resonate is they have the same chemical characteristics, okay? Because they have the same electron number and because they have the same electronic configuration. And that you can also add the same valence shell electron. Valence. Oh my god, is it with an A or an A? I always keep on getting confused. Valence electron, alright? However, they do have different physical properties. Why is this? Physical properties depend on the mass number, okay? Because they have different neutron number, that also means they have a different mass number, like explained earlier. So different neutron number. There we go. So if you ask to explain the similarities and differences in chemical and physical properties, this will be the way that you can break it down and really explain it. All right. So that's the third point done. There we go. And the last point that you're supposed to know is calculating relative atomic mass, okay? And from the relative mass and the abundances that you've been given. This is kind of part of stoichiometry, or the calculation of math units. But I have a question somewhere around, there we go, that we can use to, there's not a way of explaining it really. So there we go. So table 2.1 shows the relative masses and the percentage abundances. Okay, that's a bad lining. There we go. There we go. All right. So, of the two isotopes of in the sample, oh my god, apologies guys, that's a bit of a glitch. Of magnesium. So magnesium has isotopes. They've given out the relative masses, and the abundance of these isotopes. They didn't tell us the atomic number, but if you want to calculate relative atomic mass, the symbol for relative atomic mass is an A, capital A, small r, and they're telling us to 1 decimal place. You always have to understand and really read the instructions so that you know what exactly they want from you in order to get full marks. So here they're asking you 1 decimal places. You need to follow that. All right. So, wait 1 second. So that's what that is. All right, so in order to do that, we have our first mass of relative mass, which is 24. So that's 24 times your percentage abundance, okay? 85%. It's percentage, okay? So there's that percentage there. So you're not going to multiply it by 85. You're going to multiply it by 85 over 100 because that's the percentage. This is where some people could be confused. So it's percentage, guys, all right? Plus, it's kind of like averaging it technically, okay? And then your other one would be 26. So 26 mass isotope times 15%, okay? It is not 15 just a number, it's 15%, all right? So that's all you do. Now, if I punch into my calculator, try to do your math with your calculator as well. So let's see who gets it first. This is no competition, sorry. 24 times 85%, that would give me 20.4 plus 26 times 15 percent, 3.9. So if I add this, where's my 9? Okay, that was a glitch. If I add this together, 20.4 plus 30.9, that would give me 24.3. Okay, so this is my what? My relative atomic mass, and that is how you can calculate for any atoms, any isotopes. You don't have to know that magnesium has an isotope. you're given the table, and that's how you can really figure it out. So a little reminder, it's a percentage, all right? So that's pretty much it. This was a short video, and thank you guys for watching. See you guys in another video.